Welcome to our lesson on the area between curves. This is part 1. So the area between curves for this particular part amounts to integrating with respect to x. So we consider the region S that lies between two curves, y is equal to f of x, this pink line, and y is equal to g of x, which is the blue curve. And between the vertical lines of x is equal to a and x is equal to b, where f and g are continuous functions, and f of x is greater than or equal to g of x for all x in a closed interval from a to b. So we would divide S into n strips of equal width, just like we did when we were calculating the Riemann sums. We approximate the ith step by a rectangle with base delta x and height f of x sub I star minus g of x sub I star, based on those sample points, which is what we show in this first picture I have on here, showing those two functions and that particular rectangle based on that sample point. This is the sum from I is equal to 1 to n of f of x sub I star minus g of x sub I star times delta x. The area is a is equal to the limit as n approaches infinity, getting those increasing number of strips of the sum from I is equal to 1 to n of f of x sub I star minus g of x sub I star delta x. And the picture on here on the bottom, I should make note, shows then these different rectangles. And we can imagine that again, smaller and smaller and smaller as the number of rectangles increases. So the area between curves, this is the area A of the region bounded by the curves y is equal to f of x, y is equal to g of x, and the lines x is equal to a and x is equal to b, where f and g are continuous, and f of x is greater than or equal to g of x for all x in the closed interval from a to b, is the integral between a and b of f of x minus g of x dx. So, for example, find the area of the region bounded above by y is equal to x squared plus 1, which is the pink curve in the picture, bounded below by y is equal to x, the blue line here on the bottom, and bounded on the sides by x is equal to 0 and x is equal to 1. We have a rendition of delta x here in the middle. So, for us to calculate that, this would be the integral from 0 to 1 of, since x squared plus 1 is above y is equal to x, this would be x squared minus 1, x squared plus 1, minus x dx. And integrating this, we get 1/3 times x cubed minus a half x squared plus x. And this whole thing is evaluated between the points of 0 to 1. So this would be 1/3 times 1 cubed minus a half times 1 squared plus 1. So that would be 1/3 minus a half plus 1. That makes 5/6. So the formal area calculation that we have, when we set up an integral for an area, it is often helpful to sketch this region to identify the top and bottom curves, which is what we're showing in the picture down here in the lower right-hand corner. So the pink curve is y is equal to f of x, and the blue curve is y is equal to g of x. So f of x is above g of x. So the area as for the limit as n approaches infinity of the sum from I is 1 to n of y sub t, which will be our top equation, which is f of x in this picture, minus y sub b, which is the bottom function, which is this blue curve in this picture, delta x is equal to the integral from a to b of y sub t minus y sub b dx. But, there's a problem, right? That's presuming f of x is always above g of x, and unfortunately that does not always happen. So we could define the area of the region S to be the sum of the areas of smaller regions, S sub 1, S sub 2, and so on and so forth. And we would just add all those areas together for the total area A to be A sub 1 plus A sub 2, and all the way down to whatever number of areas that we have. And we could calculate that by taking the integral from a to b of the absolute value of f of x minus g of x dx. And we have that being that f of x minus g of x, the absolute value of that, being f of x minus g of x if f of x is greater than or equal to g of x. Or we would have g of x minus f of x, where g of x is greater than or equal to f of x. And we could kind of show that going on in this picture down here, but we have a three regions that we are trying to find the area of. We have, where that f of x is greater than g of x in the first and third regions, but the second one is not the case. So we would have that difference involved in this integration. So for example, find the area of the region bounded by the curves y is equal to sine of x, y is equal to cosine of x is equal to 0, and x is equal to pi over 2. We could see that picture here in the bottom right corner, where the pink curve is y is equal to the cosine of x, and the blue one is y is equal to the sine of x. That intersection point that we could see going on here, which will be this point here. This is where the cosine of x is equal to the sine of x. And this occurs at x is equal to pi over 4, since we are specified being between 0 and pi halves. And we could see here in the picture that the cosine of x is greater than or equal to the sine of x, with values of x being between 0 and pi over 4 inclusive. Likewise, the sine of x is greater than or equal to the cosine of x, for values of x being between pi over 4 and pi halves. So this would be the integral from 0 to pi halves of the absolute value of the cosine of x minus the sine of x dx. So since we have our two regions, we're going to break this area in half. This would be the integral from 0 to pi over 4 of the cosine of x minus the sine of x dx plus the integral from pi over 4 to pi over 2 of the sine of x minus the cosine of x dx. So this would make sine of x plus cosine of x evaluated between 0 and pi over 4, plus this would be the negative cosine of x minus the sine of x evaluated between pi over 4 and pi halves. So this would be 1 over the square root of 2 plus 1 over the square root of 2 minus 0 minus 1 plus negative 0 minus 1 plus 1 over square root of 2 plus 1 over the square root of 2. So this whole thing would evaluate to make 2 times the square root of 2 minus 2. So that's all that for part 1 of this particular lesson. Be on the lookout for part 2 and let me know if you have any questions or concerns. Thank you.